Hi, everyone. My name's Tom Wynant. Along with me today is Dr. Alan Geary. We're going to give you a presentation today on structural integrity and some of the laws that have come about and how to use testing to validate structural integrity, and then how it applies to actually construction monitoring. So add on with some slides at the back. Um, I'm going to introduce Dr. Alan Geary, and he's in Australia right now. Dr. Alan Geary started his career in the UK. He has a PhD in structural dynamics and a higher doctorate, which very few people get. He had a fundamental contribution to the topic over a 20-year period and was awarded his higher doctorate. He also won the Telford Gold Medal for his work in structural dynamics. And he's been had a long and storied career as a professor and a CTO of Stram Group. But I guess very relevant to where we are now, he started the approach of what was called structural adequacy back in the 70s when in the UK, the Ronan Point collapsed. Ronan Point was a multifamily 20-story building roughly that had a progressive collapse. And they were concerned with, future collapses and degradation of structures. So fast forward to today's structural integrity laws, and we have bookends of risk. And now we have much more aged infrastructure. So during that period, Dr. Geary worked for the BRE, which is the equivalent of NIST in the UK. He contributed to the Eurocode. He helped develop the ISO standard for structural dynamics. He went to Hong Kong and helped in the Chinese code and the Hong Kong Wind Code. He spent 15 years there as a professor and developed these methods and technologies. He was a contributor to the Japanese code through the Tokyo Polytechnic. And he also moved on to Australia and New Zealand and worked on the Australia New Zealand Code 1170 for wind requirements. And he came to the United States and he's worked on ASCE 7 for performance metrics and also ASCE 11 for the one standard that's referenced inside the current laws. And he's on supporting that effort right now to update that standard. So you have in front of you Dr. Alan Geary, who's contributed more to structural dynamics and their application to structures than maybe any human on the planet. So with that, I'm going to allow Dr. Alan Geary to say hi, and then we have a little problem, a technical problem with the slide. So I've got to move them while he speaks to them. So at some point I may pull the reins back. So Alan, why don't you say hi for a minute and we'll go from there.
Okay. Uh, Thank you, Tom. You're not sharing your screen at the moment.
Yeah, I had to get it
Okay,
okay.
that's good.
Very good.
Well, look, thank you very much, Tom, for the introduction, and good afternoon, ladies and gentlemen. I'm pleased to be able to talk to you. As Tom said, there is a lot of experience goes into what we are telling you today. So, next slide, please, Tom.
Okay. Let's see. There we go.
The experience comes not just from looking at buildings, but also bridges, dams, chimneys, and we've done a whole series of forensic investigations as well. The operations have been in the US, UK, Australia, New Zealand, Hong Kong, Brazil, Singapore, and Turkey. So we've done more than 100 structural assessments of various structures. Now, amongst these is the Cadet Chapel at West Point in New York State, 10 buildings in New Zealand, which was struck by the Kaikoura earthquake in Christchurch, and a building in New York City with large cracks, which were actually hidden. You wouldn't know they were there until you took off the covering. And then there was a school building which had degraded piles underneath it in Texas. We were able to have a look at that and say, okay, the degradation occurs only in one particular area. With the West Point investigation, we had a letter of thanks from the US Army Corps of Engineers and from FEMA. And the reason for that was that we identified some vibrations that were causing a lot of problems with the cadet chapel there. So what we said was, you can't do it as you're doing. You need to adjust that, and you have already created some cracks in the building. So they went and had a look to see, and they found them exactly where we said it would be. So in other words, they were thankful, very thankful, at the highest level here. So we have a patented technology as well, which governs this sort of thing. But that's not important. The most important thing is what we actually achieved from it. And I'm going to tell you a number of things about that and what the background to it is. So the contents of the course. First of all, it's the philosophy of testing for integrity. Secondly, visual inspections. They are very popular, and a lot of people, including those that write codes of practice, assume that the majority of inspections will be visual only. So I want to put that into a perspective. And then one of the big things is the capacity of the structure and the demand requirements which will impose on it. And then load testing. It's given as a sort of after effect in codes of practice, in standards that back up the codes. And in practice, it's incredibly important. And I'll show you something today that is particularly important. And that involves a holistic assessment. So what makes for a structure's integrity? First of all, we have the design process in which imposed forces are assessed, and they're assessed for what is likely to happen in the structure's lifetime. The loads are transmitted to the foundations, and the foundations provide a reactive force. Secondly, there's maintenance. If a structure is degrading, then maintenance can bring it back to its original design intention. Thirdly, impinging forces, if they change, or if there are other structures which adjust wind forces or the soil structure interaction, then possibly these forces can get larger. If they do, then the integrity can be a problem. User requirements, and that they don't affect the load carrying requirements. For instance, the user may put added equipment into the building, and that can adjust the structure's integrity. So the philosophy of testing for integrity is 1, collapse prevention, 2, maintenance requirements, and 3, the legal framework. And we'll cover each of these. So how do we define structural integrity? Well, it's defined in a number of standards which back up laws. So the basic definition is the ability of a structure or any of its components to perform its intended function by safely supporting and transmitting all applied loads to the ground without experiencing collapse, excessive deformation, detachment, or loss of function. Now let's look at Champlain. what I'd like to do here is show you a series of photographs taken as the tower on your right in this photograph was just collapsing. So Tom, could you go through the series of slides here? And these photographs, next one. Next one. There, now, go back one. That is actually the start of the collapse on the tower on the right. You can actually see in there, if you look carefully, that there are columns which are collapsing, and the whole of the structure is about to come down. The part in the middle, which is identified behind the K line there, collapsed to a certain amount, but on the left, the tower there remained standing. So next slide, Tom. The question here is, were there indications that a collapse was about to occur? And if you are doing a visual inspection, there are tiny signs that you have to be aware of. And on the left-hand side, where the blue arrow is, there is a horizontal crack. And the crack was caused by the pool area displacing, with effect that it created an extra stress in the columns, which you saw collapsing there. So in other words, if you're doing a visual investigation, you have to be aware of small signs like this. Horizontal crack here was, and you need to know about what causes a horizontal crack. In this particular case, it was fundamental to the entire collapse occurring. So if we are going to have visual inspections, the way that things are going with the people who are drawing up codes of practice and assessments that should be done, then these fall into the various areas, looking first at visual inspections. And those look at various different signs, various different places: an assessment area, an influenced area, load path considerations, consequence areas, and signs of damage. So the way that this is going is what I'll tell you about now. First, visual inspection, stage one. Establish the assessment area and the consequence area relative to an influence area. Next. So Florida has milestone inspections. What is reasonable and what's not reasonable? Well, inspecting every single structural element is not reasonable. Quite a lot of them are behind cladding panels. Assess all structural elements clearly. It's not possible. Assessing structural integrity using a visual only inspection is not possible. You can't draw the line between seeing a sign of a problem and the overall integrity of the structure. And using engineering judgment only, no, you need to put things together. You need to have people who have good engineering judgment, but you also need to see what the structure is doing and what its performance is. So the milestone inspection that exists in Florida at the moment consists of two phases. If structural deterioration is noted in phase one, which is mostly visual, then you go on to do a more detailed investigation in phase two. The intention in both phases is to assess that the building is safe for its intended use and structurally sound. However, saying that something is safe or not safe is something that is incredibly difficult to do. So in practice, what people are doing with the standards that are coming out is saying, okay, we can say that something is safe, but we don't want to do that. What we want to do is to say, in the same way that if you go to a doctor, you don't want to get something saying, okay, and then, oh, wait a minute, you have stage 5 cancer. So if you, the okay section should be various different levels in there, which are helpful to building owners, to investigators as well. So is the structure structurally sound? Well, it can vary, and we'll tell you about a good way to do that. One of the things in Building Code FSL 154 in Florida is that there are 2 signs of a structural deterioration occurring. First is a reduction of 33% of the lateral load-bearing capacity from the pre-damaged condition. In other words, what the design said it should be, if it decreases by 33%, you have a problem and it doesn't comply with the code. And vertical loading, if there is a 25% reduction in the vertical load-bearing capacity, then that also says you have structural deterioration. So let's look at these items: influence area, loading area, support area, consequence area, and load path area. The influence area is any area in the structure which shows a sign of damage. The influence area is any part of the structure that could share a load going to or from a damaged section. The loading area includes areas that apply any kind of existing load, prior load, or imminent loads capable of transmission to the influenced area. Now, there is an important aspect to this, and that is that imminent loads are those which include not only putting heavy things on floors, but also extreme winds occurring or an earthquake. They are imminent. They could be imminent. So they can occur at any time. And what you need to know is the risk of them occurring. And all of the design process assesses those risks and says, we will take a 2% chance of one of these imminent loads occurring in any year. If we're within that, well, we can't pay more to reduce that. Next slide, Tom. So the definitions included support area and the consequence area. So these are areas of the structure that support an influenced area, or that if they were to fail or degrade, would have a consequent effect on other parts of the structure. Like, for instance, with Ronan Point. Ronan Point had a gas explosion up on the 20th floor. It took out the ceiling, which fell on the floor and degraded the following floor, the floor, and that went all the way down to the ground. So in other words, that then becomes a consequence area. Load path. So the load occurs and it's known or assumed load path of an influence area. In practice, if you have a wind loading, it goes on to the cladding, the outside of the structure, and is borne through the structural elements down to the ground. If you have an earthquake, then you have vibrations occurring in the soil and shaking the building. So the two are a little bit different, but the building itself is the same one. So we can look at them in the same way. So what are the signs of damage? There are various. I said we don't want to go straight from safe to about to collapse. So we have a number of different areas we can put categories to them, and we can try to identify what these are. I am telling you what my impression is of the way that things are going now. So these are the sorts of things that people are talking about. So these include vulnerability, a warning, damage, defect, distress, and deterioration. So damage, an observable or identifiable characteristic that represents an apparent change to the structural integrity of an existing building or its components. Clearly, it depends on the person who's looking at it. Vulnerability is a sign of a disconnected load path. It may be an indication of overstressing. Other signs may be unusual behavior in the loading or in the influence area. A warning, a sign that's indicative of a shift, movement, and or detachment of a stabilizing or load transferring member, including the foundation. Deterioration, it's a process that results in the accumulation of changes that negatively impact on the condition of a component or an entire system. Damage, change to a component, which quite often you can see in a visual inspection, or a system by an external influence that negatively impacts its function. The system can actually involve the entire structure. The structure itself can be the system. A defect, that's a condition that was present in the original design, or it's the result of installation. In other words, maybe the design was okay, or maybe there was a problem with the design, or it was not built as the design was intended. So, in other words, a defect occurs which takes somebody with skills to identify. Distress, a condition where a component or system capacity has been exceeded. So, in other words, here we're talking about the capacity and the demand. Demand and capacity are extremely important. If the demand at the design stage is sufficient for large forces, then the capacity will be well below that. If the capacity comes up for some reason with time close to what the capacity is, then you may have a problem. You have to identify that, the demand to capacity ratio. Now let's look in detail. Here's a scanning electron microscope picture of concrete. And you can see there, it looks like early stage development of a crack. So, but that is ordinary concrete, the aging process. Next one. Concrete looks a bit like this under a scanning electron microscope. Now look in detail, you will see needle-like constituents in the cement paste. Now that's what cement paste looks like. Next slide. Now we have a sample taken from a building which was subjected to a very strong wind, a typhoon in Hong Kong. And what happens is that the concrete itself ages, it undergoes changes chemically, and you can see the broken needle-like constituents occur there. So there's a big change when large forces occur, but at the micro level. So you wouldn't necessarily see with a visual observation what was actually happening here. Scanning an electron microscope will show you a lot of detail about that. And of course, what we're actually looking at here is a force displacement diagram. We work with Young's modulus, which is used in everything that we look at. We have a design capacity, which is the end of the linear elastic range. And that's basically wind engineering. If we move a little bit further up, we have ductility, and seismic design will allow a little bit of ductility. But look at this and the implications of what it says. It says that K, the stiffness of the structure, is a constant right the way through that linear elastic range. So in other words, you can measure at very low amplitude all the way up to the design capacity, and you will have the same value of K. So in other words, measure at low amplitude and you can extrapolate to what the structure is going to tell you at higher amplitude. So we're looking at demand forces and the capacity, and we establish the capacity to demand ratio. So now we also have holistic load testing. We can apply loads directly. We can have proof loading, whereby we will add 10 or 20% of the intended load and make sure that the structure is okay. We have dynamic load testing. Now, I want to tell you, dynamic load testing contains all the information that you can possibly need. It's hidden there in the dynamics, the dynamic performance of a structure. So in other words, if you look at that and you analyze in detail, you can find out what the problems are with the structure. So we have in situ testing, and then a comparison with prescribed criteria. So the condition assessment. Now, this is the way that new standards are going, and that is, instead of suddenly saying it's not safe, there will be watch, advisory, and warning. So in other words, you're gradually going up to the level at which you really need something doing. So watch is all right. It's basically okay for the moment. Advisory will be, we can see something. You need some maintenance doing in that area. Don't just paint over it. It needs something doing. And 3, a warning. If you don't do something, you're going to have a problem. There are various definitions in laws and codes of practice in various different places. So, for instance, we have here the FBC about existing buildings. We have any building structure or portion thereof that meets any of the conditions described below shall be deemed dangerous. The building or structure has collapsed, is partially collapsed, has moved off its foundations, or lacks the necessary support of the ground, or there exists a significant risk of collapse, detachment, or dislodgement of any portion, member, appurtenance, or ornamentation of the building or structure under permanent, routine, or frequent loads. Under actual loads already in effect, like wind loads, for instance. So I want to say to you, this is the way that the Standards Committee is going, so that they do not give you just a definition of something that's dangerous and leave you to your own devices before that. In other words, there's a little way up to that. So legal changes after Champlain, basically, we are looking at a definition of structural integrity, and secondly, an amount of money available to do maintenance. So let's now look at some of the changes that occurred. And they all require a verification of structural integrity. Florida SB 154 needs a verification of structural integrity, transparency. New Jersey 2760 requires structural integrity of buildings, and that was 1st of January 2024. And there are laws now in Virginia, Delaware, California, Indiana, and other states. And there are rapid changes. Additionally, we have Freddie Mac and Fannie Mae. Their selling guide requirements for condominium projects include lender expectations for critical repairs and structural integrity. You can see it's there written in a whole load of documents. So the Florida Senate Law 154 was signed in 2023. It provides inspection guidelines and the reserves for repair and transparency of information. And it set a precedent for other states, which, as I say, have been followed. The engineer and owner requirements in the law. First, inspection of load-bearing elements, walls, and the primary structural members and primary structural system. Secondly, to the extent reasonably possible, determining the general structural condition of the building as it affects the safety of such a building. Now, let's just consider that for a moment, because this whole question of visual inspections and looking at the primary structural system are contraindicated. The reason is that much of the structural system is not visibly obtainable. So in other words, if you can look at the entire structure and find out what's going on, and as I've already said to you, dynamic structural testing is a good way to do that. So here we have a problem that occurred in Davenport, Iowa. It was a 100-year-old building. 3 people were killed. 84 families were homeless. And there are actually 200,000 buildings like this in New York City. There was significant deterioration, and they painted over the deterioration rather than doing anything about it. And then along came a wind called a Derecho. It was 126 miles per hour, 70 miles per hour average for 1 hour. And with weak buildings, the damage can be hidden. New Jersey Senate State 2760 concerns structural integrity regulations for residential structures. It set guidelines to inspect, evaluate, and maintain structural integrity. And the engineers must confirm that the primary load-bearing system includes columns, beams, bracing by conspicuous interconnections that form a path, so forces are delivered to the ground. However, if you follow the rules of ASCE, there is no civil liability for injury associated with an inspection. So in other words, you need to look at the standards that ASCE is producing. General structural integrity in ASCE 722. This is a design document, and I'll just read to you what this says because it is very important. All structures shall be provided with a continuous load path in accordance with the requirements of section 1.4.1 and shall have a complete lateral force resisting system with adequate strength to resist the forces indicated in section 1.4.2. Effectively, what this says is that the design will tell you what the load is, and the design will look at the probability of such a load occurring, and that the structural system must be sufficient to resist those loads. There is the International Building Code and ASCE 7. These two things are the basic in the United States for the design of structures. They also have in them sections about in situ load tests. In situ load tests can actually show you what's happening in the structure. And the building official or somebody investigating a structure is authorized to require an engineering analysis or a load test or both of any construction whatever. So there's ASCE 1199, which is being updated now. It was a good document, but it was not easy to read. ASCE 1199 introduced the idea of a load test, and it went into detail about what was okay. It also said dynamic response is an approved method, and the update which is occurring will include the things that were in ASCE 1199 and 1128. It'll take a year or so before it comes out, but basically the things that are in 1199, many of them are still there. I think 1128 will be much easier to read. This was a table in 1199, and if you see the red arrow there, it says dynamic monitoring. And it said it was difficult and expensive to do, but 25 years have passed since then. It is no longer difficult. It is no longer expensive. So it said in analysis and interpretation of data, and you can have dynamic load tests. You can monitor dynamic response, and this is the most efficient. And it is used, excuse me, in addition to these others, monitoring stress strain and static load tests. Again, through these dynamic tests, you can assess a 30%, 33% reduction of the lateral load bearing capacity of an entire structure, all in one go. You can also assess 25% reduction in the vertical load bearing capacity, all in one go. Load testing, though. People, when they're thinking of load testing, will think of this sort of thing. Inside a laboratory where you have a machine which produces a load and sees what the effect on a beam is. And there are various different machines which will do that. In fact, all it relies on is Hooke's law, which says displacement equals force upon stiffness. In fact, everybody does this type of test when they're testing at school. We, on the other hand, when I was with the Building Research Establishment, used a form of vibrators which introduced a dynamic force, which was equivalent to 1 ton at 1 cycle per second. And we used that on dams especially, but also you can see on the left-hand side there is a building vibrating in its fundamental mode of vibration, and it's excited by a vibrator system like this. And we actually did that sort of thing on Ronan Point. Ronan Point had a progressive collapse, is quoted in ASCE 7 as well. And I did it using this system that you're looking at now. So what we're actually saying is that we can find the capacity of a structure. And if we take Newton's second law of motion, we have an equation there, x upon f is 1 upon 8 zeta f squared m pi squared. What that actually says is that unlike what we normally do, which is to say the displacement is move the force across the right-hand side, then we can find out what displacement is going to be. And we have a lot of rules of thumb saying a particular displacement is okay. However, we're really interested in x upon f, displacement upon force. So in other words, on the right-hand side of the equation there, you can see damping and frequency. Zeta is damping, F is the natural frequency. There's also the mass of the structure, but of course, if you compare what you actually measure with what the code says it should have been, then mass stays the same. So there are only two parameters that you need to measure, damping and frequency. And if you do that, you can actually identify what the displacement per unit force is. Well, you know what the force is going to be, required to be, in the code of practice. It's there in black and white. So you know the ratio of displacement to force. So thereby, you can actually identify a risk ratio, which is the measured performance divided by the expected performance. Now, on the top right, there's a diagram which earthquake engineers use a lot, and it's actually a stress-strain diagram. In the linear elastic range, stress-strain is a constant, and then you have ductility. And when you've had a structure which is exposed to a bit of ductility, the stress-strain curve changes. So if you are measuring displacement per unit force, you find a change. All you have to do is look at it before and after an earthquake or a very strong wind, and you'll find a bit of rotation of that characteristic. I don't want to go too much into detail here, but this is basically just saying to you Newton's second law of motion, force equals mass times acceleration. And in practice, on the bottom right-hand side here, you can see statics and dynamics. If you're down at zero frequency, then you have a force that you put on and you have a displacement which occurs. If you, however, find a resonance, then you'll find a dynamic magnification factor. And that factor is 1 upon 2 zeta. So if zeta is small, which it is in structural systems, then the magnification factor, because of a resonance, can be quite large, anything up to 50 times. When we looked at the response of the Cadet Chapel at West Point, we found resonance conditions which were causing the problem. And we found a resonance condition which were not identified with the normal sort of techniques of using something down at ground level. We measured up as well. And so we could see how the structure was behaving, and we identified where cracking would occur. Next slide, Tom. So we can find damage using a dynamic load test. We look for the natural frequency and the damping. We look for mode shape anomalies, modal ratios, and modal bifurcations. Now, there's one thing in there. Looking at the natural frequency is fairly simple. Anybody can do it. It changes when earthquakes occur. The natural frequency comes down a little bit. Damping, though. Damping is nonlinear and changes much more than the frequency does. So if you're going to find that displacement per unit force characteristic, you need to know the natural frequency and damping in their nonlinear form. And being able to do that with damping is not straightforward at all. However, we've done it. We've done it on more than 100 structures, and we find that when we couple it together with fracture mechanics, the science of fracture mechanics, all of the problems that occur in the building actually jump out at you. So the natural frequency. Any structure like this, including irregular in plan, has forces acting on it which occur not just in a straightforward way, but additionally, there's vortex excitation, which sometimes causes problems with structures. That's why in this particular structure, there is a podium level which is irregular. It's irregular for the purpose of upsetting the vortices. Next slide, Tom. That's just a picture of New York City at nighttime. The damping predictors, they were originally produced in 1986 with some induced vibration testing that we were doing, identifying what that damping characteristic would be. It was copied by Lagomarsino in Italy and in Japan as well, in which they basically had a very similar equation to what was produced back in 1986. So it's used all over the world. Prediction of what damping will be. So in other words, it depends on the geometry of the structure, and particularly it devolves to the amount of mass which is participating in the mode of vibration. In this particular case, the middle diagram shows you a large crack, which only became apparent when everything in front of it was taken away. On the left-hand side is a measurement of damping, nonlinear damping. So in other words, we've got increasing amplitude and the damping value at that amplitude. Now, the important thing about this is that you can see at every single point there is a measurement of damping at a particular amplitude. And that's done by the using the random decrement that NASA used originally, looking for a problem with the space shuttle's wing. And we modified it so that it would be usable for structures. Now, that on the left-hand side is before a repair. On the right-hand side is that big crack was repaired. Also, there's a horizontal crack as well between two layers of the building. That was repaired. And in fact, using the same technique, we found damping in a three-part curve. The lowest part of that is correlated with the natural frequency. The rate of increase of that is correlated with the amount of mass which is participating in the structure. And then a high amplitude plateau, which is caused by all those things that I showed you in the scanning electron microscope, everything has given its the entire capacity. There's also a very large amplitude, a reduction in damping, and this has been shown by Yukio Tamura, Professor Tamura in Japan as well. So the Japanese are changing their code slightly to say damping will decrease with very large amplitudes. We also look for modal distortions. And if you could see here at the 28th level, you'll see a discontinuity. Instead of the mode shape, this is displacements, maximum displacements at various heights. But at 28th floor, we've got an excess, which shows a reduction in stiffness. So in other words, if we see that the capacity of the building is not what we expected, we look at the 28th floor to find out what's happening there. We look at modal ratios because we want to see if things are changing. And what we do is we look at different modes of vibration. So different modes have different frequencies. In this case, frequencies of 3.91, 5.20, 5.37, and another mode also at the same frequency. And we then look at the ratio of them and we compare these ratios as time goes by. Because very often, if we find a problem which particularly affects mode 2, for instance, the ratio between mode 2 and mode 1 will change. It will also tell us where the problem occurs as well. We also have spectral bifurcation. This is taken from a bridge in New York City. On the left-hand side, you can see a clean response, which looks like a single frequency. On the right-hand side, you can see bifurcations. The response has widened, and it's not any one particular frequency either. Let's step over this, Tom. And the next one. Okay, now these modes, as a structure gets more complex, the modes get more complex as well. These are hyperbolic cooling towers. For
Oops, sorry.
other full
Alan, I'm having a technical. Are you still speaking? Oh no. All right. We may have lost Dr. Giri on this one. Let's see. Can everybody hear me at this stage? See, we get into that. Okay. So you guys hear me. All right, very good. All right, I'll have to take over for Dr. Giri, and we were just at the end of his time anyway. What Dr. Giri was talking about here were these different modes of vibration. We actually did an assessment of a tower like this, 400 feet high, with all these higher modes of vibration at all these different frequencies. And we monitored them as they were improving and replacing concrete in a 50-year-old cooling tower. It's an amazing project, but little by little, you could see all of these frequencies tighten up and get much more stable. And when you did an analysis in the finite element model, you would see that under a 100-mile-an-hour wind, you started with like 2 feet of deflection and it worked its way down to about 4 inches. And it was a very clear example of how the actual construction was actually improving the quality of the structure. So anyway, it was a great example. Another aspect of the analysis is the vertical response. This is a fundamental aspect of structural integrity. And this spectra here was actually taken on a school in Houston, Texas. And it was an auditorium. And what we found was all four corners of that auditorium bounced around at about 5 hertz. We had never seen a response like this in our life. And what it is the spring constant of the soil responding with the structure-soil interaction. And I'm going to speak to this quite lengthy in a moment. But if you have variability at different locations or at different columns, you get a completely different geotechnical response. Well, that can speak to a very poor soil condition. In this particular case, we were able to go back to the engineer and say, gang, we have never seen anything like this in our life. And they went and did an investigation. They found very poor soil conditions and that the structure, the building, 85 years ago was built on piles, and those piles had rotted completely, eaten by termites, gone. So it ended up being a large I'm sorry, not just a geotechnical, but a foundational repair. But it was part of the school's enhancement for the structure. A very powerful tool, being able to get some understanding if you got a stable foundation or not. And we have used this across the board in all of our analyses. So this is where I was going to take over anyway. So it's okay that Alan left. And in New York City, we have 5-story walk-ups all over. There's hundreds of thousands, literally, of those buildings. And in every city in the country, even in LA and San Francisco, they have them. Seattle, Portland, you name it, they have them. The problem is, and I'll just take New York as an example, you'll very often have fill material, which is landfill material in some of these cities. And then you invariably get a compressive layer because a lot of these cities are near water because they're port cities. And then you get these compressive layers. I know Boston has it. I know Philly has it. Certainly New York has it bad. Anyway, so when you have this weird geotechnical condition, you get a strange propagation of energy and vibrations. And they will, especially if you get down to bedrock, and some of these are on piles. Now you have a transmission of energy into the structure. And what happens when you're pile driving, when you're drilling, or when even you're excavating, these different layers can cause the amplification of response in the building. And here's the crazy thing. The standard methods for monitoring are at ground level. Well, you'll never pick up amplification and you'll never understand if vertically the building is moving. So all of these things that Dr. Juries just went over about structural integrity apply every day to construction projects. So now that we have these laws, and these are the forces that are imposed upon structures, it's really logical to apply the same standards to those buildings during construction. So we have a good example of one that we did down in Florida. This is actually the Jupiter Lighthouse right over here. It's their prize asset, and they were replacing a bridge nearby. And this is an old museum, and they were going to be driving 30 by 30-inch piles, driving them right next to this bridge. And they had to make sure that this lift bridge didn't have a problem. So we did a test pile with them, and we were able to look at each one of the impacts from the pile driving. We were able to look at different parts of the structure and understand if it was moving differentially and displacing in an aggressive manner. The traditional methods of ground vibration were off by a factor of 4. We were getting 4 times amplification from ground level to the top. we had done a baseline on the structure and we understood its dynamic characteristics, and we could track to see if any of these impacts were having an effect on the structure, and also to use it to back the engineer off. So the impact of each pile, if you open up a time history when you're taking these measurements, you'll see the acceleration over time. And you can see the impact, and you get a very high frequency response that is of varying frequencies. But traditionally, the way they look at it, they pick one peak and they take one frequency off of it as if that were the only excitation and band of energy going into it. And that's simply not the case. And you can see in this time history that you got a number of different frequencies in that time history. Then you have a decay, and then you have the second impulse, and it's different than the first. So you really have a little more of a chaotic system than would otherwise be understood. So it's actually quite interesting when you get into it. And then during the process of impact, the structure will respond and the soils will respond, and you'll get a tilt response and you'll get some recovery from it. So it's actually a very interesting phenomenon. And when you're measuring down to about 1/10,000th of a degree of movement, you can actually see this in real time and see the recovery of the structure. And then you can understand if pile driving is actually causing settlement and displacement and things like that. So you get real-time feedback with that. So in this particular case, the vibration levels were low. The tilt response showed recovery. The bridge wasn't impacted by pile driving. We were able to go back and say that. So we had the dynamic characteristics. We knew how it was moving left and right and vertically. We could see each one of these impacts, and we could see how the structure responded and recovered. So it was quite an interesting takeaway. The real-time monitoring worked very well. The baseline provided a proactive tool. Tilted the piers were the critical aspect, because if you have a lift bridge and that thing doesn't come back together, you got a big problem. You're shutting down traffic. So it was really critical. We had about a 1/4 inch of variability that we could live with. So we had to be looking at very tiny tolerances. So this worked out very well. They were able to modify the means and methods for pile driving based on the test pile and this deep information. So this gets to what are the standards right now, and it goes all the way back to where Dr. Geary started as a researcher for the BRE. And when Ronan Point collapsed and structural adequacy, at the same time, the U.S. Bureau of Mines was developing RI 8507, 1980. And so during that, they were trying to figure out how do we avoid damage to structures based on vibrations. And the folks understood that what Alan was doing, and he had some coordination with the U.S. Bureau of Mines, and they actually reached out to him about some of the techniques he was using. But if you go into RI 8507 and you look at it in detail, they did the dynamic response. They measured the dynamic response to production blasting for coal. And they used spectral techniques like Dr. Geary just talked about, looking at the frequency and damping, measuring at ground level and above at the top to get the response of the structure. They talk about the risks and the limitations of their own study. They were only measuring 1- and 2-story structures, timber frame structures. They correlated ground vibrations with the potential probabilistic approach of damage. But that was not the focus of the study. That was this page right here, which kind of gave some guidelines, which I'll get into in a second. But what they did say after that study was that it was not applicable for unreinforced masonry and steel buildings. That amplification averaged 1.5 in their study. And as we've seen, Dr. Geary talked about up at West Point, we had 12x amplification. When you're dealing with these restricted structures, such as steel and unreinforced masonry, they'll amplify exponentially. As a matter of fact, they'll amplify exactly like physics allows them to, which is 1/2 zeta, which is the inverse of the damping. The lower the damping, the more potential for amplification you have. And then it speaks also that low frequency vibrations are a large risk. So now you can see that if the time history has a variety of different frequencies and you're only measuring one at the peak, you're not getting a full picture. You're not even understanding if there is low frequency content. So anyway, this has been broadly applied throughout the country. RI 8507, and this chart specifically is referenced in almost every vibration monitoring contract from bridge work to within building departments and everything. And what they use is ground vibrations, and it's actually a very good study, and it's a fair um, standard for trying to avoid damage if this is all you're going to do, but it is severely limiting. And it's, again, not applicable in many areas. But the point of this, it's not directly related to Dr. Geary's three-part curve, but it is a three-part curve, and it's based on displacement as a function of frequency. And then they also have they put it into peak particle velocity, which at the end of the day is really it's a derivative of a displacement measurement. So the lower the frequency, the greater the displacements are going to be. So it's a really important thing, and it's so relevant to today's structural integrity guidelines because they have an antiquated standard that's being used. It ignores most of the major risk criteria. Um, Now that we have structural integrity laws that allow for measuring the response of a structure, it's only logical that you doing construction monitoring should include dynamic analysis as is intended for structural integrity and as was part of this original study. So going a little deeper into the study, it looks at the natural frequency of the structure and the damping measurements. And what you can see here is that they don't even get good results. They get maybe 1 digit of accuracy, and the damping is very inaccurate and sometimes non-existent. Sometimes they didn't even get results. And that's because when you have a short time history and you have a big impulse like a blast, um, it creates a whole bunch of dynamic, a chaotic dynamic system. You get swapping of energy in different modes of vibration. It becomes very broadband. It becomes impossible to measure. So again, going back to everything Dr. Geary just said about measuring at low amplitude, that allows for a statistically valid measure of a structure's response, understanding its resonance conditions. And those resonance conditions are the things that can amplify during dynamic energy. So if you're only measuring at very high amplitude, you get messy results. If you measure at low amplitude, you get very clear, accurate, repeatable results that can be used to extrapolate up to the risk criteria. So the response data to blasts, what they were looking at is that the response at the upper corners. They had the low corners, the upper corners, and the mid wall, and they were looking at how the whole structure vibrated. They're trying to pick out the areas where it would vibrate most, where it would rack, and where a mid wall would vibrate. And it was quite interesting to understand the variations because the mid walls, a typical what do you call it, like a sheetrock wall, that's going to have a vibration of about 20 hertz. It's going to amplify in that 20 hertz range. Well, that is very close to some of the construction energy. So a lot of times the structure will get a mid-wall response and you'll rattle pictures and things like that. But structurally, you won't get a response, you know? So people get all alarmed when they get this mid-wall response and they don't understand why and they think the building's coming apart. And they could actually get some small cracking when you get that level of amplification. You got to be most concerned about is when you get the structural response, because then you're really racking it and you're imposing stresses that are much greater. Because again, going back to what Dr. Geary was just talking about, the contributing modal mass. You know, if you got a small wall vibrating, there's not a lot of mass there. It's not a lot of force causing that to move. If you get a whole structure moving, you got to move all of that mass. So you need to understand that because that is how damage occurs. So what they did in that study, they did all these blasts, hundreds of blasts over 76 structures, and with each one they created a dot and they put it into a little scatter curve here. And they said, okay, we got based on these velocities and this frequencies, this is where we got some actual damage. And so they plotted it, and they had major damage, minor damage, and threshold damage. And then they somewhat, I would call it somewhat arbitrarily, but statistically said, all right, here's where we're always going to be safe under these guidelines. And here's where we experience major damage. So up at 5 inches per second, roughly, and it's not linear, you're going to get damage. Below about 2 inches per second, based on high frequency, you're not going to get damage. And then based on the frequency, you start getting more damage at lower peak particle velocities as the structural response aligns with the ground vibrations. It's that amplification that caused the damage. They didn't do a good job of explaining that, but it really is a very kind of, I would say, I wouldn't say it's arbitrary. It was done with a statistical approach in mind. But at the end of the day, that three-part curve that I mentioned, and I'll just go back to it real quick, sorry. This is just a 95% probability that you won't get damage to an impulse function like blasting. And it goes on to caution about fatigue damage and things like that. And at the end of the day, everything is fatigue damage. So so it's really quite an interesting study, and it does give you some guidelines, but it is very, very cautioned about how it's applied. And the problem is it's been applied across the country very broadly. So,
Tom, if I could add something here, my apologies, my computer crashed a little while back. If you could go back to that diagram, that's the one.
Yep.
Yes, yep. The majority of investigations actually use this measurement of peak particle velocity within 30 inches of the ground. And as Tom says, 5 inches per second or 2 inches per second are the difference between always safe and damage. Now, the point about that is that if you ask me, I would say this is a scattergun diagram. In other words, you hold a target there and you fire a scattergun at it, and you get something like this. But nevertheless, there is something that has been drawn through at 5 inches or 2 inches, and it's used everywhere in the US at the moment. Now, if you look in detail at what came out of the US Bureau of Mines study, you'll find that actually there were lots of different structures. They were in different conditions. They had different frequencies, and that probably the damping was different. There was degradation as well. There are all sorts of other parameters which went into making up this diagram. When you compare this approach, peak particle velocity within 30 inches of the ground, with what we're telling you about, which is structural dynamics, and looking at that for indications that something is going on in the structure, there really isn't much of a comparison. There is so much more information in the dynamic response for structure than there is in something which creates this kind of diagram. Not that it was useless, it had a lot of uses. In fact, it creates some standards that we use every day. So it gives some sort of an indication. And just by the way, in the European Union, they have something which also takes peak particle velocity as an indicator of what the intensity of the vibration is. And if the intensity goes up and it goes past a threshold, then you're likely to get damage, which is all this diagram actually tells you. Back to you, Tom.
Thank you, Doctor. But yeah, no, it's really important to realize that the methodology from 1980, around when Alan was doing his work and disseminating it around the globe, They were duplicating it for this study, all for the intent of avoiding damage and understanding how structures respond. They used the same techniques that our company uses and that are in the international standard 4866, ISO 4866. And it's very specific about measuring the response of a structure and very detailed about the accuracy necessary, what standards to use, and what methodology to use. But anyway, so the point of this is they came up with a simple version for 1 and 2 story residential, and then they just came to have a 95% probability that you're okay without quantifying really much of anything. It was a very simple approach, and they speak to that. So it was effective to have a standard where there was none. But now that we have structural integrity laws and you have the capability of measuring things much more accurately, consistent with these very methods, it makes sense to do it. So the point of that study from 1980 was they followed it up in 1996 and they said, wow, we got this issue with amplification. And by the way, that's where the damage occurs. So what kind of amplification would you get if you did align the peak frequency of ground vibrations with the peak structural response? So they did a study with that, and they saw that they actually had pretty low amplification, 1, 2, and 3. But then when they did align those things, they get up to 5, 6, and 7 amplification factor. So it's important to realize that it really does apply. And in that same study, they give this chart, which I think is a good one. And it's very similar to what Alan was showing on his response spectrum, where you have, in this case, we're talking about the ratio of the forcing function with the natural frequency, where the force in the ground is aligning with that natural frequency sway, and the amplification factor when they do align. What's really important to look at is when you're off resonance, it really doesn't respond very much. It's kind of a one-to-one. And Alan can speak at length about that and it's on YouTube. But when they do align, it is, as Alan said, 1/2 zeta. And if you have 10% damping, you can get 5x on the amplification. You have 5% damping, you can have 10x. As Alan said, on structures, let's call it 3 stories and up, on 3-story structures, unreinforced masonry, we'll see 3, 4% damping. So you got the potential of 12, 15 times amplification if they perfectly align. If you got 1% damping, as Alan said, you can have 50 times amplification. Now, that's on perfect alignment. Once you get a little off resonance and they don't align so well, so you got to get kind of lucky, if you will, to hit it on the nose. But the point is the risk is there. And it's really important to understand that. And people don't understand that generally. So as Alan said, the magnification factor is 1/2 zeta. And these are exactly what I was talking about, the different amplification factors you can get. Zeta is a percentage of critical damping. The code, this is the interesting thing, and this is where there's a rub with designers in that they know that in the design process, they can estimate what damping is. And they're allowed to go to use 5% damping, 5% of critical in the design process. Now, that being said, that what we're talking about is measuring it at lower amplitude. And when it does get to higher amplitude, because of all this modal coupling and things, 5% damping is probably a conservative number for what you would achieve during a high amplitude event. But, and there's an important but there, the fact that you have very much low damping and it's a nonlinear response, and it can increase as you go up. All that means is that if you have low damping to start with, you're going to get up to a high amplitude much more quickly. And that 5%, if it aligns with the resonance, may not be conservative. And they're using a probabilistic approach with these estimates because they're looking at it from the context that a probability of hitting an exact structural resonance during a random event like a wind or seismic event is rare. I'll give you an example, though. We studied an earthquake in 1999 in Turkey, and it was about 50 miles due east of Istanbul. And during that earthquake, about 250 minarets that were part of the mosque actually collapsed. And when you look at the ground motion of that earthquake, it was 1999. I forget the name of it. Anyway, you'll see there's just three cycles that happened right around 3 hertz. And if you look at the size of the minarets, they're all the same thing. You know, these are the towers that sit on the corners of the mosques where they do the call to prayer. And those displaced exponentially with probably just those 3 cycles. And it basically took out, hundreds of these specific structures that had very low damping because by their nature, they have to. They had the right height to put them right at 3 hertz and they got wiped out. So it's really interesting to understand these principles of structural dynamics and see how they play out in structures. For Alan and I, it's been a little playground for the last 20 years of taking measurements on structures, seeing how they respond to all these different things, and understanding perfectly how logical it is, how it follows the principles of physics and the fundamentals of structural dynamics. So in that same Office of Surface Mining, Reclamation, the low frequency study, as I mentioned, this is the same thing. The number of cycles that occur and how long it takes you to get up to a very high amplification. So, when you get higher damping, it just simply won't amplify. But if you have low damping, they only have 3% here. That's actually a conservative number compared to most of the buildings we measure. So you can see it just takes a few cycles and you can get 6, 8 times damping. I'll bet you those minarets were somewhere, they're down at a damping of like 1%. And they could have amplification of 10 or 20 fold in just a couple of cycles. So a very interesting chart to understand that they cap out at some point depending on the damping. So what that inherently means is you got to measure damping. You got to get it right. You got to understand this. So here's another.
I can add to what you're saying about the minarets. The mass which is participating in their vibration has to be small, in the same way as chimneys are small, whereby you have a windshield around the outside of it, and that's all. That's all the mass there is. Now, I've made measurements of very tall chimneys to find out what the damping is. And you're talking about, yeah, they were probably around 1%. I measured at 0.5%. And that was under excitation we had a big pendulum and a hydraulic actuator working on that. The natural frequency of the chimney that we were testing was 0.462 hertz, and the damping was 0.5%. So it agreed fairly well with the estimate of what the nonlinear damping should be. But now the question is, does it increase? Does it have a 3-part curve? Well, the 3-part curve says that it races up dependent on the amount of material which is participating. If there isn't very much, it doesn't go up very much. So for minarets and chimneys, that damping stays around 0.5%. So you've got dynamic magnification factors of somewhere in the region of 50 times what you would expect.
It's fascinating to understand these principles and then see them in play out. And you could even enjoy it if you're on a golf course. You can see how the flags wave, and that's me being a nerd, but it's actually quite interesting to see how structures behave dynamically after you kind of understand these principles and can apply them. So here's a really important part that I wanted to talk about as well, and it has to do with the fundamental aspect of how these devices that are used to measure ground vibrations actually work. I don't think a lot of people fully understand it, but I had alluded to it before. All an accelerometer does is take an acceleration. It's a mass on an arm. That's all it is, a mass on an arm, and you measure the resistance. And it goes up and down. That's all an accelerometer does. And then so it goes up and down on what we call the time history, and it has what you call zero crossings. It's crossing when there's like 0 Gs, if you will. It hits a peak and then it comes back the other way, and it does some sort of sinusoidal turn like this. So that's the raw time history. But embedded in that is a number of things. The one thing they look at to get the frequency of the energy, the primary fundamental frequency of this, is they do zero crossings. They say, okay, it crossed here and then it crossed here. So that time is 1/2 of what a full cycle is. And that's the frequency of response. But here's the problem. And RI 8507 talks about it quite well in that it's a broadband response. You have energy at all these different frequencies. Just because this mass responded that way, it was impacted by a number of different frequencies, which comes out in the variability of the amplitude. So when you do a spectrum on this, you actually get all these different frequency components. The problem is this: they only report the lowest or the highest frequency because that is in the time history. So they're completely ignoring all of the other low frequency components here. So it inherently is misrepresenting the data by only measuring one frequency, and it's only measuring the one that has the smallest amount of displacement. It could be the dominant frequency, or it may not be the dominant frequency. So we did a little example of, let's say there was a frequency on a frequency. Let's say that there was a low frequency component and a high frequency component, but you use this methodology and just measure this, the frequency between these 2 points here, ignoring that there's a lower frequency on top of it. So we said, okay, if that one frequency is at 30 hertz and it was a 2G response, it would yield 4 inches per second and a 0.02 inch displacement, and it'd be minor damage. But that same time history would actually have a low frequency component that if it's at 2 hertz and it's a 0.5 G response, it's actually 15 inches per second, and it would be catastrophic damage. And that's we're just making a point. This is a mechanical excitation taken off the internet. But we did go through the math on this to say, what's the impact of ignoring low frequency content? And if that low frequency content excites a structural resonance and you have amplification, you got a triple whammy. You're underreporting the frequency, you're underreporting the potential of displacement, and you're not even measuring in a place where you could get the most damage. So we got an enormous risk here that is inherent in the process. To be fair, probabilistically, you're not going to see it that much. But here's the thing. We've been doing it for 20 years. We see it on every project. We just don't see it every day. And this is what we did for the Army Corps and different people. We stopped their work because we're looking at the spectrum and we're looking at the broadband response and we're looking at the total displacement of the structure. So this is what our clients have come to appreciate. But now with these structural integrity laws, it's incredibly much more important because you can't damage structures and owners shouldn't get their structures damaged. And now they're responsible for making sure they don't get damaged. So we have a different legal environment. So it directly relates to structural integrity. And again, these are antiquated methods that should be using more appropriate methods. One other relationship between acceleration frequency and velocity. And again, it goes back to that issue of time history. If you have a 40 hertz response of 0.2 Gs, that if it's at 40 hertz, you get 0.31 inches per second peak particle velocity. If it's actually at 4 hertz, you get 3 inches. So it's a 10-fold factor. This is really the energy in construction. This is what you're going to see in that raw time history if you had to get the dominant frequency out of it. But if there very well could be a structural response embedded in it, and it has such a bigger influence. 4 hertz is a very logical response for like a 3-story walk up. A 5-story walk up might be down at 2.5 to 3 hertz. So we have been on those projects and seen these structures move aggressively back and forth. People sometimes run out of the buildings And the guy says, oh, listen, we only had 0.31 inches per second. And that's because they're just not measuring it in the right place. So there is a big risk there to the society that's relevant to all of this. Um, so why should engineers perform these sorts of baselines on structures? Well, you want to understand the structural integrity laws and the requirements to make sure that they have enough capacity, and understand if a structure is weak. These are all in the codes. You want to understand if the structure is behaving in a manner consistent with structural integrity, meaning that it distributes forces. And let's say you see an anomaly in a moat shape. You know that you have some sort of structural anomaly in that structure. Now you can do a deeper dive into it. I would say 9 times out of 10, we're validating that the structure is okay. But it's surprisingly, it's not a small number of structures that where we find issues, like we did in the school in Texas, and where we did it in New York City with that big crack. We usually get to tougher structures, but these weaknesses exist. And then you can change the means and methods, or you can change the type of maintenance for regular structural integrity. So monitoring at ground and amplification is necessary. You need to be able to do that. And that can only happen when you understand the dynamic characteristics, and then you can track it from there. You can track performance. These methods can also track settlement, because you're looking, these same accelerometers, because of their sensitivity and capability for this advanced analysis and very low amplitude measurements, they're tilt meters. So they can track 1/10,000th of a degree. So now you can correlate all of this energy, 200 samples a second at all these different locations, and look at it in real time. And it's like getting an EKG on a structure. You can see the patient on the operating table. You can see if he's moving this way or that way. You can see if he's getting changes to these dynamic characteristics. And it can give you an indication of risk. Are you amplifying? Are you getting large displacements? Are you getting slow progression settlement? Can you see, a trend over time? And then you can separate it out from thermal effects. So it really creates an incredible wealth of information that can be used as actionable information to avoid damage, avoid problems, and it ties directly into structural integrity laws. So with that, let's see, we have the test coming. It's 5:33. So we got mostly done with all this. We got all done with this. And I think we could take any questions. Is that appropriate, Alan?
Yes, actually. Have you got some more slides on the end of this, Tom?
Well, there's some here. Do you want to speak to these?
Yes, please. Yep.
Right. Well,
what we have here is a series of slides which will tell you what we were doing on site and how we actually identified some of the particular problems. This is the Cadet Chapel at West Point. You can see that there's a bell tower. There's the nave and the two transepts. What we found was, and I think we've identified something before. We found down at the ground the peak particle velocity was relatively small. We had a 12 times amplification when we were up in one of the transepts, which was furthest away from the explosions which were being done to prepare ground for a new building. So under that circumstance, we saw that the nave was swinging around, the transepts had their own vibration frequency a little bit, so the interface between the transepts and the nave were where we thought cracking must be occurring. So we actually said to people, you mustn't do this. We've measured down the ground and we've got a 12 times amplification up high. And so They had a look. They found the cracking inside that area between transept and the nave, and that's why the Army Corps of Engineers decided that they would say thank you to us. This is the response in those different modes. What we've got at ground level, and we've had a factor of 1.0 there, and then measuring at different places: Tower East, Tower West, and Tower North, and the bell tower. You can see the bell tower had almost no amplification to it. But Tower North, that was in the vertical direction, it had a 10 times. To get that, what we did was measure the PSD, power spectral density of the response, and that gave us a 10 times factor. But if you looked at individual time histories, you found anything up to a value of about 12 larger than the ground value of the response. Wellington City, we had the Kaikoura earthquake, and Tom led a team going into Wellington and looking at 10 different buildings. And they gave us 10 to have a look at. They didn't say whether they were good or bad, asked us what we thought.
Well, let me expand on that a little, Alan, because they were
Okay.
10 city buildings of ranging in age from 120 years old to about 30 years old. They were of all different size and heights, but they were critical to the city. They said, if we get a big earthquake, we're very worried about these buildings because we're going to have to use these as shelters, and we got to make sure that they're okay. And they said also, one of these buildings we're a little worried about. Could you tell us which building that is? And we said, okay, we'll take a look. What had happened was the Kaikoura earthquake actually happened about 100 miles away. And it was a very violent, the second biggest earthquake in New Zealand's history. But it happened in the middle of nowhere. But that wave came up and it propagated. There's actually a fascinating time history on how that wave propagated and what happens as waves propagate like that. The high frequency content gets filtered out and you end up with low frequency waves. So when it hit Wellington, it was about like a 0.1 or 0.2 G, relatively low, but it was at 1 hertz. So what happened, based on the orientation of the buildings and their natural frequency, some of them really, really rocked. And when I say they rocked, they displaced a lot because that ground frequency, that ground wave aligned with the structural resonance, not just a fundamental, but the second order mode. So it affected buildings that were like 6 to 10 stories and buildings that were like 20 to 30 stories because that was the second order mode at that 1 hertz frequency. So it's really interesting. They actually had to demolish 30 buildings when an earthquake hit 100 miles away. And they did not understand why certain buildings got hurt and others didn't. Now, you could have two buildings that are exactly the same, and they could have different dynamic characteristics. And if the one with dynamic characteristics that align with the ground, it could displace tenfold more. And you will get that level of damage on top of it. So that's what happened. And they said, which one of these 10 buildings got damaged? So we did our analysis. This is the earthquake, and this is Wellington up here. And you can see it ripped the ground like a zipper. It actually caused a 15-foot displacement, and it took areas that were underwater and shot them up above water. There were fish flopping around. It was absolutely amazing, and it ripped right along that fault line all the way to Wellington, which made them quite nervous because this fault has now fractured and is now closer to Wellington. So anyway, they've got something to be nervous about. But it was quite a violent event at the time. This was the weak building. 400 city workers worked there. And we did our analysis. It was like doing this assessment using these techniques. Took 4 hours. Not a big deal. But we took measurements at the top of the building at all different locations and down the stairwells. What came out of it? We found one area of the building had a very clear weakness. The overall stiffness, Alan mentioned that if you lose a 30-year capacity, you have a significantly damaged building according to the Florida building codes. In New Zealand, if you lose a 30-year capacity, that is a threshold for repair. If you lose 2/3, you got to tear it down. They're the only country that we're aware of in the world that has a got to tear it down criteria. We found that this building was at 1/3 of its capacity, meaning that, holy smoke, this thing is really not in good shape. So here's what happened. One engineer came in and did an assessment of it visually and said it has 80% capacity. The city could say, well, we don't have to do a thing. The next engineer, equally as qualified and well-heeled in New Zealand, who was doing other structural assessments, said, no, you got 1/3 of your capacity. So two qualified engineers gave the same building on the same day a completely different analysis. And the impact was, one said you got to tear it down. The other said you're fine, let everybody back in. And they couldn't live with that. So they asked us to tell them out of the 10, which was the bad one. Well, we said it's this one, it's damaged here, and you got a failed member on the 3rd floor. And sure enough, they tore a wall off and they said, wow, those diagonals had failed. So it was a pretty powerful example. It created a condition where they could repair the building. They made other decisions, but in any event, it was quite an interesting project. So, Alan, anything else on New Zealand that you want to fill in with?
No, no. You've explained that very nicely. And in fact, it was the visual inspection by two engineers showing that you can get very different results from that. And you compare it with our dynamic signature monitoring, and we came up with what was actually an identification. You'd better do something with this now. They really loved it too.
So I think an important aspect to this is that, if you do a deep dive analytically on a structure, you're going to do a finite element model. And in that model, you're going to put all the material properties, you're going to put all the dimensions, and you're going to put all the assumptions about the materials itself. You can degrade those models if necessary to reflect damage, but those models are going to predict the dynamic characteristics that we measure. One of the tasks that we do with this information is we calibrate models. And by putting those measurements in, you can see what they're really going to perform like. So the Millennium Tower in San Francisco was a building that got significantly damaged due to settlement. Hadn't been through an earthquake yet. So they had to verify for the courts the capacity of the structure. So they did a finite element model, and they took some results from their seismic monitoring system. They had to go back 7 years to get enough information to get accurate, detailed information to calibrate that model. We can do that in a day with these techniques. So what's evolved technologically is the ability to calibrate these models to make them correct, so that you can use them for risk analysis and detailed quantification. You could even use those models for long-term management. But at the end of the day, the measurements are far cheaper than putting together a very detailed model. And again, they can get done in hours with a lot of upside. Alan, I'm going to present this last one, all right? And then that'll give you...
I wanted to finish up with this last one. I think that this is, let me just say, the Kosciuszko Bridge felling. In fact, what we were doing was looking at the behavior of a structure and seeing whether it had structural integrity or not. And we had great. They were going to pull the bridge down anyway. So we worked with them to produce an artificial earthquake and take a look at the response of the building to that. Well, it wasn't quite as simple as that. Over to you, Tom.
Okay. Well, so this is an old industrial building, about 60 years old, right next to the old Kosciuszko Bridge, which is now gone in Brooklyn, New York. Each one of these spans weighed about 400 to 500 tons. They're much bigger than they look. You know, the depth between the girders and the deck was probably 20 feet. Very big truss system. They were going to blow out the bottom truss cords and just fell it right onto piles of dirt 10 feet from this building. So the owner was obviously very nervous, and they said, "Can we do something to avoid this?" They were very, very nervous about damaging this building because it's already in the state of damage. So this speaks perfectly to the whole issue of structural integrity. And a little side note, ICC 1500 is coming out, and that is an inspection requirement for every building, all buildings, industrial, commercial, you name it. So this whole issue with structural integrity that came about in residential housing and condos is now across the board. That's going to come out in a year or so. In any event, we went there and we did a baseline on this structure. Well, going back, these are the cords, this is the deck, and these are the piles of dirt. And again, they were just going to drop it right on top of that. And they assumed that it was a normal building and that it would displace by 1.8 inches per second. So they were saying basically, we're going to keep this under damage levels. And they base that on it being a normal building. So they're assuming some of the fundamentals. Well, what we know is that not all buildings measure the same, and you need to physically measure it to understand that. So these 10-foot berms were going to catch this. It's going to drop about 60, 70 feet, 400 tons, 10 feet from the building. So as Alan said, it's very much like a little earthquake. So what we did, we're missing a couple slides here. That's unfortunate. There's a couple really good slides here that should have been part of this. We did before and after measurements. So what we found was that the fundamental mode should have been 6.3 hertz based on some normal predictors on frequency, and it was half of that. So it had 50% of the stiffness or the frequency relevant to stiffness. And that is going to create actually a fourfold increase to the same force in displacement. And then the damping initially was very, very low. It was 0.9%. What that tells you is that a few cycles will actually cause a lot of amplification. So it should have been somewhat closer to what the frequency was. So in any event, we put this into what we call a risk ratio. As Alan mentioned, this is the thing that is patented. And we come up with a return period, which if a normal building should displace at the end of the elastic limit based on a code compliant event, a 50-year wind, 150 miles an hour, what does something with half the capacity and a very low damping criteria? Well, that wind that would take it outside the elastic limit is about a 78-mile-an-hour wind. So what we're basically saying is it should be here, but it's actually here. So it's a fundamentally weak structure. But after the felling of the bridge, there was a lot of damage. You could see cracks opened up. You could see all kinds of problems. What did the measurements tell you? Well, the frequency went from 3.22 to 3.15, so it reduced by about 2% or 4% stiffness. The damping, which is a level of damage, it's an indicator of damage, went from 0.9 to 1.5%. That went up 50%. And that is the much more sensitive damage indicator. And that changed the risk profile to a once in 2-year event, meaning a 66-mile-an-hour wind event, which we just got here over the weekend with the storm. That could cause further damage in the structure. So it's a pretty powerful capability to be able to say, listen, here's what you think you have. When you measure it, you got a severely compromised structure. Change your means and methods and avoid damage. So that's what they did. They actually increased the berms from 10 feet to 25 feet. The energy that occurred at the top of this structure was not 1.8 inches as they had anticipated, far above that. And that's why they did get damage. But now we could quantify what the damage is. We can tell them exactly how these dynamic characteristics changed within an hour and give them this information as feedback. So anyway, it was a win-win because we avoided catastrophic damage. We got some minor damage and they worked it out. So anyway, so why would you do this? Well, for structural integrity and for construction monitoring, it's a essential due diligence step, but it limits liability for everybody. Using this technology saves money, and it helps everybody understand what their risk is, and so you can mitigate it. You can identify weak buildings before damage. You can prioritize budgets for things that need to be fixed. You can ensure that the work that was done met its intent, or a new building met its intent, and it's performing as expected. It's a could be some quicker way to reoccupy as well. So these objective measurements will help assure safety, compare all structures based on risk. Now that you have a criteria, and we didn't get into it, but there's a lot of metrics in the code about performance, about what the normal stiffness is, what the minimums are. They're all in the design codes. What sort of torsional response you need to have, how much of a displacement between stories can you get? All these metrics for a well-designed structure are there. And now all you got to do is take the measurements and compare to those metrics. So that gives you a risk profile that validates if it's code compliant. So anyway, it's the appropriate use of system theory. And again, in ASCE 11, it says if you have a methodology that gives holistic system information, those are preferable. So it falls into line very nicely to take these measurements, quantify the risk, complement visual inspections to maintain structural integrity for all of our structures. So it's an objective mechanism to improve our building stock for long-term sustainability and resilience. So that's what the intent of all this was. And now that we have structural integrity laws, that's how these tools, which again, there's an international standard, it gets done in different countries at a much greater level, but it's time for us with these new laws to start deploying them. So anyway, let's see. I'm not going to speak to that one. I think we're kind of done, Alan, because do you want to speak to these concluding remarks?
The concluding remarks really say that what we've been saying to you is that there is a change in the law all over the place, not just in the United States, but it's changing all over the world as well. And
Sorry.
they actually tell us now that we need to have an identification of structural integrity, and that that relies on the skill of people doing inspections, doing the analysis of structures as well. But what we can do is actually use our skill set, our logic, and use dynamics. It's very rarely identified as something that we must do, but it's always there to say, yeah, you can use it if you like. But when you actually find out that dynamics carries so much information, then I think it's a very good idea to be able to do the displacement per unit force measurement using structural dynamics. Okay, ladies and gentlemen, thank you very much indeed for your attendance. And if you do have any questions for us, we'd be happy to answer them now.
Okay. Well, I think we're done. So with that, you guys have a quiz to take, and let's see, there's one chat here. Let's see. Greetings, questions, comments, issues. So yeah, you can get into that chat and actually ask any questions that you have. We'll get those. And I think with that, we're done. All right. So, Doctor, I'm going to sign off, and If anybody would like to reach out to us, we're at straamgroup.com, STRAAMGROUP. And on our website, we have a whole bunch of information about structural dynamics. There's a whole wealth of history here, and it's very relevant. These ASCE documents and also the RI 8507 and the OSMRE documents are there. So feel free to get that information if necessary. So thank you all for joining.
Thank you.